Hello, miniKanren workshop. I'm Dmitry Rozplokhas, and I will present our work on certified semantics for disequality constraints in miniKanren. Last year, on the first miniKanren workshop, I presented our project on development of mechanized formal semantics for miniKanren. Such semantics can be used as a simple way to describe search disciplines in miniKanren, independent of the specific version of the language. And it also can be used to prove formally some useful properties of the language, including logical soundness of its extensions. I then presented our initial results, namely operational semantics for the core miniKanren, which reflects interleaving search canonical in miniKanren, and our proof of its equivalence to denotational semantics, which shows that the interleaving search is complete in some general sense. After the talk, there was a question whether this semantics can be extended to the language with disequality constraints, and I answered yes and said that it's mostly a technical work. However, when we started working on it, it turned out that there are some interesting aspects to it, and we decided that it deserves another talk on the second workshop. So here we are, and today I will, during today's talk, I will briefly revisit our definition of semantics, but we'll mostly focus on the what disequality constraints bring into the picture. Let's start with the question what disequality constraints are. Basically, it's a constraint that is complementary to the standard equality constraint in the miniKanren. It specifies that in the result, all bindings of logical variables should not turn two given terms into syntactically equal. It can be very useful to write relations in miniKanren, in particular for case analysis on equality. The basic example for this is the following lookup relation, which relates a key and a value in some dictionary as a set, as a list of pairs. When defining it, we want to distinguish two cases when the key, when the argument key is equal to the key from the head of the dictionary, and we already have our right value, and the case when they are not equal and we need to continue search in the tail. Disequality constraints are allowed to describe it quite naturally, and without disequality constraints, there is no simple way to write it. For this reason, disequality constraints is one of the earliest and the most useful extensions of miniKanren. And in miniKanren, it is implemented in the following way. Along with the current substitution, some constraint store is threaded through computations. It keeps information about disequality constraints and is updated when search meets equalities or disequalities. Let's now move on to our formalization of disequalities. Here is the base language we will reason about. It's a very simple version of miniKanren where terms can only have constructors and logical variables inside, and there are 6 types of goals which should be familiar: equality and now disequality of two terms, conjunction and disjunction that we have instead of standard cand operator, introduction of a fresh variable, and a call to some defined relation. We first give denotational semantics, which formalizes the mathematical meaning of the program. It can be constructed, it can be defined in a standard way by constructing the List-Herbrandt model. We interpret each goal as the set of representing functions which map logical variables to ground terms. And the definition of denotational semantics is quite natural, as you might expect. We interpret equality as a set of functions, of representing functions that turn two terms into syntactically equal, and the disequality is complementary to that. Conjunctions and disjunctions are interpreted as intersections and unions, and so on. Next, we give operational semantics, and it should reflect one concrete search procedure. In our case, it's a canonical interleaving search for miniKanren. However, there are different ways to implement constraint stores in different versions of miniKanren, and we would like to be able to cover all of them by our semantics. So to do this, we add an abstract layer in our semantics with definitions related to constraint, with abstract definitions related to constraint store. We can we then use it in our definition of semantics and can later substitute different concrete definitions there to get different implementations of, to get semantics with different implementations of constraint stores. The abstract layer includes the following things. We assume that we have some definition of constraint store objects in the context of the current substitution, and we assume that we have a way to interpret them denotationally. We also assume that we have some initial constraint store and two operations manipulating with them. Operation that adds constraint to a store, and the operation that updates the current substitution. Both operations can either return updated constraint store or signal fail if the constraints are violated. The semantics is, we described the semantics as a labeled transition system with observable answers, which means that we defined a set of states of the set of search states and transitions between them, and then each execution is represented by a path along these transitions. The base state is tasked to evaluate some goal in some environment of substitution, constraint store, and the counter of logical variables. We can also combine states with sum for parallel execution, and combine state and the goal with a product for sequential execution. And we also have terminal state for completed search. Some transition can be indexed by answer, which is final environment. This represents an answer that we get on this step. We defined the transitions by inductive rules. All the work with disequality constraints happens in the rules for basic goals. Specifically, when evaluating equalities, we try to unify two given terms and then update the current substitution with the unifier using our abstract operation. And when evaluating disequality, we just use another abstract operation to add a constraint to a store. Rules for other type of goals are rather predictable, in particular for disjunction. In particular, we transform disjunction into a sum and a conjunction into a product. And the rules for sum and products specify interleaving in the search. It's in a standard way. In sum, we make one step at a time in each state, and in product we evaluate the goal in environment of all answers that we get from evaluation of the state. Now, when we have two different semantics, we proved that they are equivalent to show that our search procedure covers exactly a mathematical model of the program represented by denotational semantics. To do this, we need to give a denotational interpretation to the answers, and it is just all representing functions that are consistent with both substitution and restrictions of constraint store. And then we can formulate the equivalence in the following way, to say that union of interpretations of all answers that we have in our path equals to denotational semantics. We prove we mechanized proof of this equivalence in Coq, and as a bonus we get we can use now Coq extraction mechanism to obtain different to obtain certified interpreters for miniKanren from this proof. But of course, we need some conditions on this abstract operations for search for proof of completeness to work, and we came up with a list of the following 5 conditions. They state that initial constraint store and our 2 operators should be consistent with the given denotational interpretation of constraint stores. These conditions are exactly what we need in the proof of completeness, but at the same time, they just state that intuitive meaning of these operations, so we expect them to be provable for all reasonable implementations of constraint stores. We now we provide 2 examples of such implementations. The first one is the simplest implementation we could imagine. It's simply stores all pairs of terms from encountered disequalities and never uses them. This implementation trivially satisfies our sufficient conditions, but it of course is not. It of course isn't very practical because, among other things, it is inefficient since search doesn't use negative information in any way, and it can return answers like this, in which final substitution contradicts final constraints. Such answers doesn't represent any solution, so it doesn't affect completeness of the search, but still it's not seems not nice to have them. Our second example implementation are more practical, and it's basically the formalization of the initial implementation of Disequality constraints in miniKanren. Here, each constraint is represented as additional substitution that contains a variable binding that should not be satisfied. And loosely speaking, add operation just unifies 2 terms and adds a unifier to the store, and update operation tries to unify every constraint tries to apply additional substitution to every constraint and then unify it again. But actually, it should be written down more carefully with considering all the cases. But there is no problem to write it down formally, and it is the full formal definition is in the paper. We proved sufficient conditions for this implementation too, but it required some additional work because it's true only for kind of nice substitutions that we have in miniKanren. And the property that we have that we need is intuitively that once binded variables never appear in the result of substitution again. The formal definition again can be found in the paper. Besides besides establishing correctness of the different implementations, we can also use our framework to reason, to prove some properties of different implementations and compare them. And we can use this handy principle for this. We can make our reasoning in denotational context, where it's usually much easier, and then use our equality result to transfer it into operational context and have the same result for our have the same properties called in our implementations. The examples of such properties include the presence of contradictory answers that I described for trivial implementations. So the trivial implementation can have them, and the realistic implementations, and the realistic implementation doesn't have them if the number of constructors in the language is infinite. And whether it's true depends on the specific version of miniKanren. Other useful example of properties of property that we can prove is some optimization of correctness of some optimization of disequality constraint implementation. For example, there is a known optimization when we can discard a constraint. When in the realistic implementation we can discard some constraint if it is subsumed by some other context. And the following lemma justifies it, and this lemma is trivial in a denotational context. So to wrap up, in this work we presented operational semantics for parameterized by implementation of constraint store. We provided a list of 5 sufficient conditions on this implementation for search to be complete, and provided 2 examples of suitable definitions that satisfies this conditions, and get certified interpreters from the mechanized proofs, and gave example of some of its provable properties. That's all. Thank you. Thanks for watching.